Chapter 6, Section 7, Problems Involving Motion. Well, we're going to look at these types of problems in here with the other examples. I'll probably break these down into separate videos. So let's look at these motion problems. It says when we end up, first thing you need to remember is that these formulas, which really is just solved for different variables here, distance equals rate times time. Really it's all derived from the fact that rate is distance over time. That's what a rate really is. Usually we express rates like 60 miles per hour, which is really 60 miles the distance over one hour, right? So rates we kind of assume that the denominator is 1, and we do that. Well, and that's where they derive the rest of these. If you want to know what the time is, you take the distance and divide it by the rate. And if you want to know what the distance is you take the rate times time. And rates, again, rate is another word for fraction. That's because reality, this is the beginning formula. They set up this idea of a rate, which is distance over time. So you need to remember that when we're getting into these kinds of problems. And so let's look at this first one here. It says on her road bike, Olivia bikes 5 kilometers per hour. That's a rate faster than Jason does on his mountain bike. Actually, the rate is more than the 5 mile an hour, right? In the time it takes Olivia to travel 50 kilometers, Jason travels 40. Find the speed of each bicyclist. So we want to set up, when we familiarize things, we want to set up an equational, right, or an algebraic translation of this more complex problem here. So what they start doing is say, well, let's guess a little bit here. Let's see what happens with the numbers and those kinds of things, and it'll show us really how we're going to manipulate or set up our expressions and equations and so on. So they say guess. What if Jason was traveling at 10 kilometers per hour? Well, then what would be Olivia's speed? It would be 5 kilometers per hour faster, right? So we'd end up with 15. Well, in Jason's time, let's say if it is, they said 10 hours, right? Or equals 4 hours. If he goes 40 kilometers at 10 kilometers per hour, it'll take him 4 hours. Well, Olivia's time is 50 kilometers per hour at this other rate, and she'd go 3.5 hours. These times are not the same, so I didn't get lucky and guess the correct answer. But this really helps familiarize with these kinds of problems. So it's a very good thing to go through to set up what we're going to need to know to do this. Well, and then part of it, what I call all the time is, well, what are we looking for? What are they asking for? They want the speed. In other words, the rate is what they're looking for. What's the speed of each bicyclist? So let's reread this with rates in it. And if I first define the variable and say Jason's rate is R for rate, right? What would be Olivia's rate? Well, she's going 5 kilometers per hour faster, so it would be 5 plus Jason's R, right? The rate that he's going. So they start setting up the expressions that represent these different people, right? That's what they're talking about here. Organizing it, very good idea again. So here's Jason's mountain bike. He goes 40 kilometers at this certain rate, so the time would be the distance divided by rate, or 40 over R. Olivia's road bike is, she went 50 kilometers, and this represents her rate, which is 5 kilometers per hour faster than Jason's. So what would be her time? Her time would be that 50 kilometers divided by this rate of Olivia's, which is r plus 5. Well, since we know that the times are the same, that's what they say, well, they end up taking the same amount of time. Well, if this is time and this is time, they're saying these two things are the same, we can set those equal to each other and solve for r. So then we carry out this equation of 40r equals 50 over r plus 5. A good strategy again is to clear the fractions, take the LCM of r, the factors r and r plus 5, which would be r times r plus 5, times both sides. It'll get rid of all your fractions. You end up with this r over r makes 1, and here you get r plus 5 over r plus 5 equals 1. Notice that they're not showing all that work again, but remember we're actually making fractions equal to 1. That's how you simplify fractions. And if you attempt this and you don't end up with, or you end up with still having a fraction, then you've probably done something wrong. So now we have a simpler equation to solve. They add negative 40 to both sides. They get 200 equals 10r, and then take 1/10 times both sides, you get 20r equals r. Now what does r mean? R is the rate of Jason, right? So we go back and think about this back in the original deal. So if I have Jason's rate I've determined is equal to 20 kilometers per hour, I go back and say, what does this mean now? Well, how fast would Olivia be going? So would be 20 plus 5, and then we'd say, well, how much time does it take Olivia to go 50 kilometers at 25 kilometers per hour? It'd take her 2 hours. And Jason travels 20 kilometers at 20 kilometers per hour. It would take him 2 hours. That checks to say, hey, that is our two answers right there. But really, I didn't go back to my work or anything else and try to check. I try to go right back to the original application that we're trying to solve, and put these numbers we think are solutions in there, and then check those, right, and make sure that they work. Let's look at example 4. A Hudson River tugboat goes 10 miles per hour in still water and travels 24 miles upstream and 24 miles back in a total time of 5 hours. What is the speed of the current? Okay. Now at first glance you say, I don't think I have enough information, but let's look at this. Let's try to figure out what's going on here. To do that, and you say, well, let's throw some numbers at it. Let's say the current speed of the current is 4 miles per hour. So the tugboat speed going upstream, which means going against the current, would be actually this 10 miles per hour minus the current speed, the speed of the river flowing, right? And we'd get 6 miles per hour. If the tug was going downstream, its actual speed would be in addition to that stream current, or I get 14 miles per hour, right? Well, travel time upstream then would be 24 divided by 6, right? And we'd find out it'd take 4 hours. Travel downstream would be 24 over 14 miles per hour, and it takes us almost 2 or 1.5 hours, 1 5/7. Well, these times are not the same, and that's part of this problem, is we have a matchup on time again. So the guess can be wrong, and we make some observations. C is the current's rate in miles per hour. In other words, they start defining some variables here so we can translate this into algebra. So if C represents the current of the river, right, how much speed there is, if you're going upstream, it's going to be that 10 mile an hour minus this current that I don't know, called C. and the tugboat speed downstream will be 10 plus that current speed of C. And we know what the time is. The total travel time, which is upstream downstream, is takes 5 hours. Now, you don't have to get this elaborate with drawings, but this is a pretty good picture to write. I'd probably draw a line that, hey, I'm going to go 24 miles up and then back 24. But the rates when I'm going up are 10 minus C, and when I'm rate coming down is 10 plus C. Well, we can translate that into our motion problems using distance equals rate times time, or in this case, time equals distance divided by rate. So here's the actual rate of the tugboat when it's going upstream is 10 minus C. Well, the amount of time it will take then would be 24 divided by that 10 minus the current, or C. And when it's going downstream, we have a different speed or rate of 10 plus C, so you take 24 divided by 10 plus C. Well, these two things are equal to time. Now, what did they tell us, though? We got to go back. It isn't really that they're equal to each other, because they won't be equal to each other. It's sure going to take less time going downstream, right, than it would be going upstream to go the same distance. But we do know that the amount of time to go up and down is equal to 5 hours. So if this is the time of going upstream and this is the time of going downstream, they should add together to get 5 based on what they've told us about this situation. So then I can solve this equation for C, which is going to tell me what the current rate is. Now again, they clear the fractions by using the LCM. They end up with this quadratic situation where I can factor this. Remember the factoring rules: when we have anything to a degree 2 or higher, we got to make it equal to 0 and try to factor, so we can figure out what those factors would then be, possibly 0 to make it 0, right? Well, we set this equal to 0. They solve for, they add a negative 500 to both sides, and add a positive 5c squared, to both sides. Well, then I start factoring. Look for common factors first. Yeah, I have 2 terms. After I common factor, I have 2 terms here too, but then when I have a double term, and the only thing I can factor are difference of squares and sum of cubes and differences of cubes. So this is a difference of squares because 4 is something squared. So I can factor that into C minus 2 plus C plus 2. And so we end up with these solutions here. 2 of them actually, where C, the current speed is 2 miles per hour, or the current speed is a negative 2 miles per hour. And in the way we've set up this problem, it doesn't make sense to have a negative rate, right? So the current speed should be 2 miles per hour. Now you could go back to the original and then check that whole thing and put in those 2 differences in speed. We know that when you're going upstream, you're really going 8 miles per hour, and when you're coming downstream, you're going 12 miles per hour. And you can see if the numbers work. So motion problems are often much easier, much simpler to solve if the information is organized in a table. They've shown this both times. Is we have distance, speed, and time, or distance, rate, and time, right? And they start organizing the information. So when we look at this one, it says Tara runs 1 kilometer per hour. Well, that's a rate, right? Faster, they're talking about rates. And Tara can run 20 kilometers in the same time it takes Cassie to run 18 kilometers. Find the speed of each runner. Well, we start putting some things into this table. right? You put the things that we know. Well, here is we have to define something. So they say, well, let's make Cassie's rate R. And there's a reason you do that, because there's a pretty good expression right here, 1 kilometer faster than Cassie's rate. So what would you put here for A? A would be this R plus 1 would be Tara's rate. Can we put something in for Tara here? They already did. The distance for Tara that she runs is 20 kilometers, so they put 20 there. And here's a distance for Cassie, so you'd put 18 here. And what else happens here? You know, if we go back to the original, it says that they have an equal time, right? What is the speed of each runner? So they say it happens in the same amount of time. So I don't really care what this is other than what this formula creates, and then I can set them equal to each other. Okay. Here's the answers that they put in for those options. So really what they're doing is they're trying to guide your practice specifically to making these tables fall together right, which is a very good way to organize your work and work with these things. So next video will be about problems involving proportions.